All right, those at home, I'm not really sure when this got cut off, but the video did stop recording. So let's just move on to the example problem in the interest of time. Sorry about that, everyone. Again, if you need to blame someone, Kurt's a good scapegoat. Okay. So let's look at example number 3. Again, this is an FRQ from a previous AP exam. A motion sensor and a force sensor read the motion of a cart along a track as shown below. The cart is given a push so that it moves towards the force sensor and then collides with it. The two sensors record the value shown in the following graphs. Now, what this doesn't tell you, and which an astute student last period actually pointed out an inconsistency with, is if we define the initial motion of the cart as being in the positive direction, which the graph shows, right? The graph for velocity versus time for the initial part, the initial motion before the collision with the force sensor, it's in the positive quadrant. It's in the first quadrant. So what direction do you think the force should be pointing during the collision? During the collision. Between the cart, which was moving this way, it collides with the force sensor and then ends up moving this way. It should be to the left. It should be negative. So that force versus time graph, if I had written this question, I would have said the force versus time, the force probe reads the magnitude of the force versus and plots it versus time. Because really those forces for that entire part of the motion, for the entirety of the collision, should be negative. They should be pointing this way because the object is moving this way. And Newton's second law experiences an acceleration because of that collision, which makes it go this way. So the force must be in the opposite direction. So someone pointed that out. I didn't even really point that out until we got the mathematics ended up giving us a negative mass when we were being very careful with our vectors. And that's when, oh yeah, we probably should have had a better question. But it's from the College Board, so you can't expect too much. All right. So part A, given all that stuff, part A says determine the magnitude of the change in the cart's momentum during the collision. So I'm going to say the change in momentum. We don't have to do X and Y directions because it's only one direction. Change in momentum is mass times the change in velocity, final minus initial velocity. What's the mass? Yeah, it's a trick question. Yeah, we don't have the mass. So how are we supposed to find the change in momentum if we don't have the mass? Was that? What we we can find the impulse, right? If we have the force, now the force does change, but we have a graph. And so with that graph, we can determine the impulse by finding the area. Yeah. The area of a force versus time graph tells us the impulse. And by the impulse momentum theorem, we know the change in momentum is equal to the impulse. Right? And the impulse is equal to the area under force versus time graph. Now I'm going to put under here in quotes because if the graph actually dips into the fourth quadrant, that's a negative impulse. Those are negative force values. Okay. So all I need to do is figure out the area. And that will tell us the change in the impulse. The magnitude of the impulse, though, because again, those forces should technically be negative. And so when I look at this shape, notice it's not a curved line like it would be in reality. In reality, it would be a curved line that we would then be able to model with some function and then do that integral thing if we have it in Logger Pro. But we can model a spike like that with the triangles and trapezoids and stuff. And so we had to look it up last period, but I remember now the area for a trapezoid. So I have a triangle and I have a trapezoid. So the area here, I know this equals the impulse, and I know the impulse equals the area. Well, the area here of the triangle is just 1/2 base times height. The area of the trapezoid is 1/2 base 1 plus base 2 times height. Now, don't fall into this pitfall. Those graphs, those graphs have different divisions. Like a lot of people would say, well, the base of the triangle is 2 and the height of the triangle is 3. But someone that would say that isn't reading that graph carefully enough. Because if you look, the base of this triangle goes from 0.34 to 0.36. So the base of that triangle is 0.04. What's the height of that triangle? 30. Right? Again, some people would put 2 for the base and 3 for the height. They're not reading what each individual tick mark represents. This is 0 there. Sorry. I get so caught up sometimes. Yeah. Oh, I quit. Have a good day. All right, base 1 then. You just tell me because I don't want to mess up again. Now, base 1 goes from 0.33 to 0.37, so that is 0.04. Base 2 is the same as that guy, 0.02. And the height of the trapezoid is 10. All right. And that, obviously very easy to do in your head. That comes out to 0.6. Oh, no, it's total of 0.6. I did that all night. I don't remember that from last period. So it's 0.6. That's calculating the impulse by finding the area, but the question is asking what's the change in the cart's momentum. So if I was being very nitpicky here, I would say the change in the cart's momentum is 0.6 kilograms meters per second. But again, because we do have a visual here, that change in momentum should actually be negative, right? The question did say, what's the magnitude? So when it says, what's the magnitude, you really don't care about the vector nature of this. So I can erase the little vector symbol. But technically, it should be a negative change in momentum.
Shouldn't you always put the absolute values when talking about magnitude? Or is that
Yeah, in physics C or in calculus-based physics, you will use the absolute value. Technically, it would be like this. The magnitude of the change in momentum is 0.6 kilograms meters per second. All right, number B. I don't think we're going to get to C, but we'll just start tomorrow with that. Part B says, what's the mass? Ah, that one thing that we thought we were going to be able to use in the beginning to figure out the change in momentum. Yeah, now we just substitute the change of momentum in for delta T. We know the initial and final velocity, at least we can get it from the graph. So I just say change in P is mass times change in velocity. Well, what is our initial velocity here? And you can approximate here, they would accept a range of values. Well, I'd say 0.22. Initial velocity is 0.22 meters per second. Final velocity is?
I think it's about negative 0.18.
Negative 0.18 meters per second. And this is where we realized, because I of course knew, but I was just seeing if they were going to catch on. It's not true. This is where we realized, oh yeah, this doesn't make sense unless we have a negative change in momentum. Because then you calculate a negative mass, which doesn't happen. So our change in momentum needs to actually be negative 0.6 for this to make sense. Looking at the diagram, it's easy to see that that has to be the case. But mathematically, it doesn't make sense if it's not. Because now I'm going to have mass times final velocity, which is negative 0.18, minus initial velocity, which is 0.22. So negative 0.6 equals negative 0.4 times mass. Now the negatives cancel whenever I divide to find the mass. And I get that the mass is 1.5 kilos. And part C is easy. We'll start with tomorrow, but part C says what's the change in kinetic energy or how much energy is lost. We just figure out how much kinetic energy it has at the beginning, and then figure out how much kinetic energy it has after the collision, and the difference in those kinetic energies tells you how much energy was lost in the collision. which means it just disappears from the universe, right? No. Well, we actually have time. Why do I keep getting my times mixed up? Any questions? Actually, we will save that for tomorrow because I want to make sure we understand. So sometimes, and by sometimes I mean very often, questions will ask, what's the mass? And you'll have to determine the impulse first. Guys, you'll have to determine the impulse first and then equate that to the change of momentum and then find the mass. Sometimes you have to find the force, the average force, by first determining the change of momentum and then dividing that change of momentum by the time, and that gives you the average force. So this is a great problem that indicates like how you can find one thing by finding the other thing and then use that to find another thing and all that good stuff. It incorporates all of the stuff, the area, the change of momentum equation, and the impulse equation, and then equating the impulse and the change of momentum. Okay. And again, part C, we'll just kick it off tomorrow with that, but it's pretty easy. It's just find K equals 1/2 mv squared. Obviously, 1/2 m times 0.22 squared is larger than 1/2 m times 0.18 squared. And that little bit of missing energy, you know where it goes? Mostly heat, right? Just so you guys know, what do I mean by heat? Temperature, the physics definition of temperature is the average kinetic energy of a system of particles. So whenever things get hit, like this hand, I hit with this hand, this kinetic energy stops. And that kinetic energy transfers into, this hand doesn't move, but that means that the atoms in this hand are now moving faster because they've absorbed some of that energy. And so the temperature of this hand goes up a little bit, which takes the kinetic energy of this hand.
When something's just moving, does that change?
Huh?
Movement just change the speed of something?
No,
It should-
not as a, no. It would have to be slowing down in some way.
So
And notice that as an
the
object,
one faster just don't have, just because it's the one faster doesn't mean it has higher, right?
no. But if it's moving, if it's losing energy, say due to air resistance, it's increasing the
Let's
temperature
see,
of the air.
Like in a vacuum, something going fast, does it increase?
No.
So if you slap a chicken hard enough, you can cook it.
Yeah.
Yes, somebody did a video on that.
Yeah. I don't know if practically you can make that happen in reality, but theoretically, yes. If you can keep it perfectly insulated so you lose no heat after you've input the heat into it. But the thing is once it gets hot enough, you actually have to hit it with a velocity that's higher, or the particles in your hand have to have a higher velocity than the average velocity of the atoms within the chicken. I would think. I don't know. Yeah. Because heat always spontaneously flows from the hotter object to the colder object.
Usually. But it's funny because we're.
Oh, well, unless you do work to make it do the opposite.
We're on a really low spectrum.
That's how refrigerators work. You want your refrigerator work, you got to pump heat out of the refrigerator. So you got to take heat from a cold object and put it into a warm environment, which requires work, right? Which is why you got to plug in a refrigerator, otherwise it doesn't work.
Interesting video I watched where it talked about quantum atoms. It was like, okay, so looking at how heat is actually transferred, it is possible for a cold thing to get colder, even though you put a hot thing on it. But the chance of it happening.
Oh, you're talking quantum
so
mechanics then.
ridiculously low.
You're talking quantum mechanics.
Yeah.
In the quantum realm, anything's possible. It's just not likely. What's up?
Hey, I want to ask you a question really quick about the exam. There's a question that says that we stick a spoon in hot soup, and the end that is not touching the soup becomes hot. Is it still just conduction?
Mhm.
Okay, cool. What is it though, like conduction from the hot end to the?
Yeah, each part of the spoon is in physical contact with another part.
Okay, cool.
Yeah.
All right. Because that one seems to be being missed a lot. and,
Oh, really?
Probably explain it, and then I just wanted to make sure that.
Okay. Yeah.
Thank you.
Uh-huh.
Gonna come in?
Give me 1 second. I still gotta wipe off the tables.